Hey, good evening, everybody. Hey, I wanted to test out Vieta's results with a polynomial with complex coefficients. So you can see right here that we have a linear term in this quadratic expression that has a complex coefficient 3 plus 3i, and then also a constant term. Now, you do got to get used to thinking of this guy right here as this entire object right here would be your constant term. It has no dependency on x. Now, I discovered something. I don't know how often it holds, probably just when you're dealing with integers, but you can use kind of the equivalent of the rational zero theorem when you're working with complex coefficients, complex numbers. Now, so it's kind of nuts here if you take a look at this. You don't know what B is. You don't know what C is. You don't know what D is. They're unknown complex real numbers. I don't know if I really have to specify that or not. We can call them complex numbers if you want. But we're supposed to find all the zeros of G when we don't even know B, C, or D. And that's kind of crazy. This kind of blew my mind when I created the problem. But it turns out this is a remarkable amount of information to be given. This is a lot of specificity here. This is a second degree equation with known constants in all the coefficient locations. You got a 1 here, and you know you have the complex numbers here. It's a factor of g of x, and that means that if this is a factor of g of x, all of its zeros are going to be factors of g. All right. Now, and that's what I said right here. We're going to set f of x equal to 0 because that'll allow us to locate the zeros, its zeros, and then those zeros in turn will be half of the zeros for g of x. So that's what we're doing right here. So we set f of x equal to 0. Again, since any zero of f of x is a zero of g of x, owing to the fact that f of x is a factor of g of x. All right. Now, so the constant term again, this guy right here is the constant term. And notice that it factors kind of nicely here. All right, minus 4 times the quantity 1 minus 3i. So what we do is we speculate that this might be the factorization. And surely enough, if you know, 4, this constant 4 times the constant 1 minus 3i is certainly all of this up here, right? And you can verify that when you multiply out the rest of it, you get the 3 plus 3i. Now, you could have messed around. This could have been 4 and maybe 3i minus 1. But you remember how when this was just a regular constant, you took its divisors, right? And then, you know, for example, let me just give you a concrete example here. Just in the good old days, you know, let's say you have x squared. Let me do this one. Plus 3x. What do we need here? Maybe minus 10. Okay. Now, notice this factors into x plus 5 and x minus 2. And you see, that's just easy. You learned that in middle school, right? Some of us did, at least. All right, so screwing around in middle school. But anyway, notice that the plus 5 and the minus 2 are divisors of negative 10. Now, that's not something you stop and think about too much. You just get the answer on to the next problem, right? But you see, in much the same way, minus 4 and 1 minus 3i are divisors of this constant term. In the same way, these guys are divisors of this constant term. See, complex numbers have a lot of the same properties, you know? So anyway, that's how we get this. X plus 4 is one of the factors, and x minus 1 minus 3i is the other factor. All right, so just right off the bat, we know that the solution set for f of x is minus 4, comma 1 minus 3i. Now you say complex numbers always occur in conjugate pairs. Here's an example where it didn't occur right off, but we know that 1 plus 3i will have to also be a factor of the bigger polynomial g of x, right? Remember, there's a well-known result that complex zeros can occur. They have to occur in conjugate pairs. That's a proof. I don't even know if I can prove it, but I know that it's true. All right, so that's why when we go down to g here, we still have all of these zeros, 4 and 1 minus 3i, but we also added this extra 0, right? Now notice this wasn't part of this solution set, but it has to accompany 1 minus 3i. All right. And that's what really makes this thing fly. Okay. It's really cool. The conjugate pair result is what makes this kind of an easy problem. Now, the next thing that makes it easy, if you want to call it that, is there's not an x cubed term right here. You have 0x cubed located right here. Now, y'all, if you don't know much about Vietas, I don't have time to talk about it, and I can do a video on that if you want. But what we know is that this 0 right here means that what we call sigma 1, which is the first symmetric polynomial, okay, it has to be equal to 0. Okay. And again, you can't keep these videos, for me to talk about that in depth, it'd take another 5-6 minutes. But it turns out this is called an ESP, the symbol for an elementary symmetric polynomial. And it's just the sum of all the variables. Okay. So right here, so since there's no x cubed term, this sigma sub 1 has to be equal to 0, but it's also equal to the sum of the zeros of g of x. All right. So we already know that minus 4 is a 0, 1 minus 3i is a 0, 1 plus 3i is a 0. X sub 4 is the only unknown. Notice how the imaginary parts cancel out nicely. We get minus 4 plus 2 is minus 2. All right. And then that implies that x sub 4 has to be equal to 2, right? If you got minus 2 resolving in this part right here, again, these guys cancel out. So minus 4 plus 1 is minus 2. So we need a plus 2 right there for this to be equal to 0. Again, y'all, I know that's swallowing quite a bit if you've never heard of the elementary symmetric polynomials or know anything about Vieta's formula. But in the name of brevity, we're just gonna state it as a fact. And so what we get is x sub 4 is equal to 2, and there is our solution set. That's our solution. And y'all, to me, I'm still relatively astonished. Never did we have to determine B, C, or D. The fact that this guy right up here was a factor gave us a ton of information. It gave us these two zeros, and then the fact that conjugates, complex numbers occur in conjugate pairs, gave us this third 0. And once you have 3 of the 4 zeros, Vieta's result. This is called Vieta. Let me make sure I'm spelling it right. V-E-I-T-A. And that would be apostrophe. Vieta on this thing. Vieta's results. And also, by the way, this would be your sigma sub 2, sigma sub 3, sigma sub 4. And so, again, it's kind of a hollow feeling not to know what B, C, and D are, right? But we have, you can rest assured, and I may do another video, we'll go through finding B, C, and D. Right now, knowing these zeros, you could just substitute the zeros in and do elimination and figure out what B, C, and D were. But that's kind of the beauty of the Vieta's formulas, is if you know the zeros, you don't necessarily have to know the coefficients. And if you know the coefficients, you don't necessarily know the zeros. It's weird how that works, But in any event, I hope you enjoyed that. Let me know if it interested you, and that there's a ton of problems you can do on this. So have a good night.